Momentum is the concept where it is a mass that is in motion. And the equation for momentum can show that, and that momentum, which is represented by lowercase p, is equal to the mass times the velocity of whichever it is traveling. Momentum is going to differ from energy in the fact that momentum is a vector value, meaning it has both a magnitude and a direction. And the direction of momentum is going to be the same as an object's velocity. So if an object is moving to the right with a velocity, their momentum is pointed in the same direction. Whereas if it is moving to the left, the momentum would move in that direction as well. Momentum is also going to be measured in something called kilograms meters per second. It's the mass times the velocity. So kilograms for my mass, meters per second times for my velocity. And there's no special term like newtons or anything like that, or joules for momentum. Momentum, though, does give us the idea of you don't have to be big to have a large momentum, or you don't have to be moving fast to have a large momentum, right? So we can have an object, two different objects of two different sizes, where with this having a much bigger velocity than this object, and these two could have the same momentums, right? So momentum of object 1 could equal the momentum of object 2, just based upon how we find the value of momentum of mass times velocity. So a big mass and a low velocity can have the same momentum as a small mass and a large velocity. The conservation of momentum is a concept that we're going to look at, and this is a concept that we're often going to deal with when we're talking about collisions. So when things collide or when two objects run into one another, momentum is typically the physics concept, which is going to help us understand the resulting motion. So conservation of momentum, just like energy, is the momentum of a system must be conserved. And we underline system because the individual pieces of a system doesn't have to conserve the momentum, but the entire system itself must. So that means that the total momentum initial has to equal the total momentum final. And we can think of our collision as our equal sign. So our equal sign is going to represent our collision. So whatever is happening before the collision must equal after the collision. And so, like I said, the momentum of objects or the pieces of the system will change, but the total is conserved. So the total is simply going to be the momentum of 1 plus the momentum of 2 plus the momentum of 3 equals the momentum of 1 plus momentum of 2 plus momentum of 3. And this really is the equation. Again, this is our collision right here, right? And so this is the total before, and then this is going to be my total after my collision. When we're talking about conservation of momentum, there are typically a number of different types of collisions, which we're going to look at. And they all follow the same pattern of the equation that I just showed you. It's just we can group things a little bit differently. So one collision is called an elastic. An elastic collision is defined, and really this is a perfectly elastic collision, is defined when the momentum is conserved, as well as the kinetic energy of the objects is conserved as well. And so typically what you'll see is, you have an object which is moving along a surface, and then they collide. So this object is moving, object 1 is moving towards object 2. There's going to be some collision, which again is my equal sign. And then what we'll see is we'll see object 2 moving away from object 1, and that might be stationary after that collision. So if we're writing our equation with this, we could say momentum of 1 initial plus momentum of 2 initial has to equal the momentum of 1 initial, or excuse me, that's final, plus the momentum of 2 final. So that equation has to hold true for the conservation of momentum. Now, if it's elastic, we're also going to have this kinetic energy is also going to be conserved. So you could say 1/2 mu1 squared plus 1/2 mu2 squared. It's going to equal 1/2 mv1 squared plus 1/2 mv2 squared. And this is just saying initial velocity, final velocity, final velocity. Those two have to be conserved as well. The other type of collision is inelastic. In this case, only momentum is going to be conserved. The kinetic energy of the objects will not be conserved. In an inelastic, they could bounce apart. They can also stick together. So in an inelastic collision, might look something like this, where we have object 1 moving towards object 2. They are going to collide, and then they're going to move together, stuck. So what that's going to look like is momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final. Now, if we look at this object, both of these are going to be moving with the same velocity. So as we write this out, it's going to be mass 1, velocity 1. Let's actually just use a u there. u1 plus mass 2, u2, their initial velocities, equals mass 1 plus mass 2 times their velocity. And we can do this because the two individual objects have the same velocity, so we can factor out that velocity and simply get those two added together. But notice that my initial equation is still the same. All this is doing is saying, okay, this would be mass velocity 1 plus mass velocity 2. And these two velocities would be the same, so I can factor those out to get mass 1 plus mass 2 times whatever the resulting velocity is. Our last type of collision is one called an explosion. Again, this is an instance where only momentum is going to be conserved, and it's basically the opposite of an inelastic collision, where we have two objects which are either stationary or they're both moving together in some way, 1 and 2. There is then some explosion, and now we could have object 1 moving to the left, and now object 2 is moving to the right. So they've exploded apart. Again, we're going to have momentum 1 initial plus momentum 2 initial. It's going to equal momentum 1 final plus momentum 2 final. And just like we just saw, these two objects, because their velocities are the same, we could then write this as mass 1 plus mass 2 times my initial velocity of the total equals mass 1, velocity 1 plus mass 2, velocity 2. So I'm setting up this equation every time in a way that I'm simply adding the momentums before the collision. The collision is my equal sign. I'm adding the momentums after the collision, and then I'm breaking down this as mass times velocity and mass times velocity. And with this, I should be able to solve for any of these unknown values.